Sure, sure. Uh, Hello everybody. Thanks for coming and hope you all having a good day. So a big disclaimer before I present on this topic. I'm not working on this topic. I'm working on the consequences of this topic. This is something that has been fascinating me from a couple of months. So I decided I'll utilize this platform to present on this topic. As you can see, the topic is about the Antarctic sea ice loss, the abrupt decline, and its future risks. Interestingly, the background photo here you can see is somewhere near Denman Glacier, where this photo was taken during 2021, where 70% of the sea ice was lost, which is why this ship was able to make land close to the coast. So this was something unusual. And one very interesting thing is the name of this ship is Laura Bassi, and this ship holds the world record for the southernmost latitude ever reached by a vessel. So the latitude is around 74.5 degrees south. Well, of late, we are seeing newspapers, but unfortunately, the entire 95% of the footage is either Pakistan or Trump or something. But the last 5%, which often goes unseen, covers news something like this. Every other week or every other day, we see news about climate change, extreme rainfalls. But what happens down south and up in the Antarctic and at the Arctic often goes ignored because, well, there are no observations and we rarely make station once a year or twice a year. But even those rare amount of observations that we have, we see that the Antarctic ice has been completely shutting off. I mean, it's losing at a very faster rate than what was expected from climate models. Before going into the dynamics, before jumping into the numbers, before jumping into the trends, I just wanted to show this GIF, which shows you the seasonality of sea ice cover around Antarctica. The colors in red, blue, and green are the sea surface temperatures. The white is the sea ice cover. So the maximum sea ice extent is in the month of January and February, and the minimum sea ice extent is in the month of July and August. It's exactly flip of what we see in the Northern Hemisphere. Contrary to the Arctic, you see wherever we have a minimum of sea ice extent, at the same location we have maximum because of the influence of the interhemispheric the seasonal influence. But interesting thing we notice is that in the Arctic, the maximum sea ice extent is about 14 million square kilometers. On the contrary, the climatological extent of sea ice in the Antarctic is a bit higher. But the lower extent of the Antarctic sea ice during the southern hemisphere summer season and the Arctic minimum during the northern hemisphere summer season almost coincide. The values are almost similar. So what is causing this extra melting of Antarctic sea ice? One big reason what is causing that extra melting is in Arctic you have land cover, more or less the land surrounding the Arctic ice sheets and the ice glaciers, but here it's all exposed to the ocean. So ocean plays a very crucial role, I mean, both in the Arctic and Antarctic, but in the Antarctic it plays a major role in controlling the sea ice cover. Here, I have shown the monthly sea ice volume, and color is, I have colored it with different years. The darker color represents the the current years. So you can see that in 2024, this is the year 2024, and this gray line is the climatological average taken during the satellite period. So you see how far off we are from the climatological average, both in the summer and in the winter. But the winter time sea ice extent, the difference is way larger than the summertime difference. So this hints us to the mechanism that there is less sea ice formation than increased melting. So this raises a question that what happened? Something happened. You're not able to form sea ice. Because you're not able to form sea ice, you're not able to melt the sea ice. If I look at the global, the northern hemisphere average ice extent, more or less around the Arctic, we see that it has been declining since whenever we have been taking observation. And this has been of interest from a very long time. But Antarctic, on the other hand, it was increasing at a rate of around 1% per decade. In fact, if you see, in the year 2014, 2013, and 2012, we had the record high Antarctic sea ice cover. So we were thinking that if the Arctic sea ice indeed shuts off the AMOC, now again, why I'm talking about AMOC is because these sea ice trends, this sea ice cover and this sea ice reduction and increase on a longer time scale, they control the overturning circulation. So the more the sea ice you have, the more is your convection, the more is your bottom water transport, and your overturning circulation is kept healthy. Once the sea ice formation is shut off, your convection is shut off, your bottom water transport is shut off, your overturning cell tends to shrink away. So we thought even if the Arctic component of the convection is being shut off, we still have the Antarctic, which is trying to keep it healthy. But unfortunately, something happened in the winter of 2015 or the early 2016. We see an abrupt decline in the sea ice extent. And these are the record low Antarctic sea ice cover taken from the year 1979 to till date, the entire satellite era. So we see that the top 5 record lowest Antarctic sea ice cover has happened in the last 4, 5, 6 years. And so before going into the Antarctic sea ice, let's first check how Antarctic looks like without the sea ice. So this is the bare image of Antarctic sea ice. So this basically tells us the land cover. So the brown is where the land is above the sea level, and blue is where the land is below the sea level. And this is how if you take a photograph of the beneath the ice sheets of the Antarctic land ice, you see that these white patches corresponding to the West Antarctic, somewhere near the Ross Sea and the Amundsen. Ross Sea is here, which is the Pacific sector of the Southern Ocean. Amundsen Sea is somewhere here. This is the Weddell Sea, which is the Atlantic sector of the Southern Ocean. And this is your Drake Passage, just for the geographical context. So we see that the West Antarctic is more or less a big block of ice, which is just floating on top of water. And the block of ice is sometimes kilometers thick. On the contrary, the East Antarctic, you have a proper land. On top of the land, you have layers of ice sitting on top of each other. The layers of ice may be kilometers thick, but still the ice block, which is in the West Antarctic, is much thicker than the ice sheets and ice shelves that sit in the Eastern Antarctic sector. So now, since I have shown you a context behind how the ice sheet and the land looks like, the X-ray image of the Antarctic looks like, we will see how ocean could play an important role. So this is a schematic I have made. So this basically shows all the major processes that drive the oceanic overturning circulation. So the major process that is present is you have ice shelves which melt, which form deep water convection because of dense water tends to sink at higher latitudes. The dense water tends to flow north. Because it flows north, something has to come and replace it. So this is a principle of continuum applied on a very large scale. So because this is sinking and going north, because you have tropical and subtropical warm and saltier waters replacing the cold and fresh waters, these warm waters tend to have some kind of an effect on the sea ice and the ice shelf. And what is that effect? So earlier I showed you the West Antarctic is just a big block of ice, sometimes kilometers thick, right? And sitting bang on at the sea level. So if I supply continuous, if I have a continuous supply of warm waters, the block of ice tends to melt away. So you see a rapid melting of land ice. This plot shows the melting rate of the land ice, averaged from I think 2004 to 2018. So you see a rapid ice loss, land ice loss in the West Antarctic, not so much anywhere else. And because you have a rapid land ice loss, you tend to have an increase in sea ice production. This is the trend of the sea ice concentration. Blue is positive, brown, orange is negative. So everywhere else you have a reduction in sea ice, except this patch where you tend to have an increase in sea ice. So this mechanism this schematic kind of explains the mechanism. So in the West Antarctic, you have a big block of ice. You supply warm and salty waters. The land melts and melts. So this process is called ice calving. So the ice block calves. It becomes fast ice or floating ice. The fast ice and floating ice further, as it cuts off connection from the land ice, the ice block, it floats and becomes an ice sheet or sometimes an iceberg. So yeah.
Say in one sense it's ice is melting and
Yes, that's what I'm explaining here. So if you increase this mechanism, you tend to melt away the ice block more and more. As you tend to melt away the ice block, you tend to produce these ice sheets or ice bergs more. So if this reduces, this will increase. That's what's happening here. So the land ice is reducing. Yeah. Yes, it's getting thinner and thinner, and it's going offshore. So that's what's happening here. The land ice is melting, but sea ice is increasing. This is the predominant mechanism that is causing the changes. This is a photograph which I've taken somewhere near the Amundsen Sea. So you can see the block of ice. I mean, this is just above the sea level. Below the sea level, the entire height of this block is around 4 to 5 kilometers. And this is how calving looks like. So you tend to melt away the ice from the bottom, forming cave-like structures. So this is the process of calving. I think at the same location, if I'm not wrong. Well, that's fine. We have supply of warm waters from the tropical, subtropical ocean basins because of the overturning circulation. What big difference does it make? Ice is supposed to melt, ice is supposed to form. That's fine. But the big difference is that because we have a surplus, because we have no ice formation post 2016, because of the warm water supply, ice is not forming. Because ice is not forming, the sea surface properties tend to become warmer and saltier around the Southern Ocean, which it should not. Because the sea surface is becoming warmer and saltier, it is inhibiting the process of sea ice formation. One such practical example of this application of this example is the opening of the Weddell Polynya in the winter of 2016 and 2017. So Polynyas, this is a photograph of Polynya taken somewhere in the Weddell Sea. So Polynyas are basically, you have entire ice sheets and you have a hole in the ice sheet, which is open to the ocean. So it's open ocean convection. And why this hole is there? That hole is present because you have supply of lower level warm waters, because there is some kind of topography below it. The warm water is steered because of the topography and it upwells along the topography. So that upwelled warm water along the topography melts away and eats away the sea ice, thereby opening polynyas. And polynyas are so rare that the last polynya we saw was in the year 1974, 1975, and 1976. And then again, we are seeing the same polynya in more or less the same location in the year 2016, 2017, because of the abrupt loss of sea ice or the thinning of the sea ice. This schematic more or less explains about how the polynya forms. You have deep waters, the circumpolar deep water, which is the tropical warm waters coming from the northern latitudes, entering into the ice shelf regions, calving over the sea ice, forming fast ice and ice sheets, and then you have your polynya formation because of topography steering. I think they should have put a topography, but that's fine. Well, what if, again, this brings us to the conundrum that the more the sea ice, the more the convection. But if I have lesser sea ice, should the convection stop? And that's what you're seeing. This is from the CMIP 6 simulation model ensemble mean. The black line is the ensemble mean. Mind you, these CMIP 6 models, they don't have a meltwater physics, which means they don't have ice sheet and iceberg, the physics of the ice sheet and iceberg in them. They don't solve for ice sheets and iceberg. But what if I put the ice sheet and iceberg in some climate model? And this is how the overturning circulation change looks like. If I have the effect of ice sheets and icebergs, the overturning circulation tends to shut off much quicker and much faster than the models without ice sheet and without icebergs. So you do see a large impact these ice sheets and icebergs play in controlling the large scale overturning circulation. Well, since most of these models were uh, uh, done on a cold start, or they were started on a, I think this was started in 1990 or 1991, which was considered to be a neutral year all around ENSO, IOD, and other indices. It was supposed to be a neutral year. But what if I run a climate model, initializing my model at the year 2016 when ice was melting away? So they have tried that model, running that model. So they have run the model, initializing the sea ice concentration that was present during 2016, 2017. Unfortunately, the model shows a recovery of sea ice uh, as you march on time. But we don't see that in observation. You do see a rapid decline on the other hand. So this model says that you have a recovery in sea ice, your sea surface temperature and your sea surface salinity tends to recover. I mean, it was warmer and it slowly becomes colder and vice versa. But this is what you're not seeing. You're not replicating the observation. In fact, in the observation, you're seeing a much bigger decline. So what could be at play? I mean, are we solving the wrong physics? So for that, we need to have more observation. Just going once or twice to Antarctica to take ice cores or measurements will not be sufficient. Since we have made much more advancement in satellites, we can use the uh, wireless technologies to map and uh, measure the ongoing dynamics in the both Antarctic land ice and the ice sheets. Well, that being said, there are plethora of mechanisms that operate the loss of sea ice and land ice. For example, some of them are, I'll tell you, one example is the buttressing effect. Buttressing is if you have a big block of ice, and since you're calving away the ice from the bottom, the top half of the ice tends to have a normal force, which tries to stick to the big block of ice. So that big block of ice tends to exert some kind of force on the land. So that example is called that phenomena is called a buttressing. So if that effect of buttressing is gone, it will if the more your buttressing stress, the more sinking your motion in your sea ice, the more it is susceptible to melt away because of the supply of warm water from below. So that tends to have a large effect. And other example is the effect of geothermal heat. I mean, there are plethora of mechanisms, but at the end of the day, all of these mechanisms combined tend to have a larger effect in the West Antarctic ice sheet. That is because it's a big block of ice. It's not a land, it's a big block of ice, which is very prone to melting from the tropical and subtropical waters. Unlike the Eastern Antarctic uh, uh, ice shelves and ice sheets. Now, this I have taken from a paper by Gasson and Kiesling. They show how the paleoclimate Antarctic ice sheet cover looks like. So what they have done, they have used the dissolved oxygen proxy to check for the ice, the presence of sea ice. So the more oxygen you have, if you have greater oxygen, it is more exposed to the atmosphere. If it is more exposed to the atmosphere, your sea ice has to be less. So you see that from the past millennia, so we are in a state where the exposure to the atmosphere is very high compared to the last 60, 65 million years. And even in this state of low sea ice, we are currently in the year where sea ice is at Antarctic sea ice is at its lowest. So if I further extend this graph, if I zoom into this graph showing yearly variation, it might look something like this. Well, that being said, you might think you're sitting in the tropics. What effect does Antarctic ice have on tropics? I mean, it has a plenty of effect. One effect is the sea level rise. So sea level rise is broken into 5 components. The larger component which explains the sea level rise is the thermal expansion coefficient, because ocean is warming, it tends to expand. So that contributes to around 39–40% of the expansion. The other 3, which are more or less equal, is the land water storage, which is the river runoff and the land precipitation. Your glaciers, your Arctic ice melting, which has been melting from decades. Your Antarctic ice sheet surprisingly has only 10% contribution. But mind you, this was during the period 2006 to 2018. What if I draw the same pie chart from the year 2020 to 2025? Do you think this percentage, this contribution will increase or decrease? That's an open question. Next, since ocean models are very iffy when initialized from the year 2016, 2015, 2017, how do we resolve them? It's not only about sea ice, it's also about the biological losses, your overturning slowdown, your land ice retreat, your ice shelf losses. So how do you solve all these processes? That's an open question to be answered. Since there are a lot of open questions to be answered, but there is one big question at play. The question at play is, post 2016, there has been a rapid decline in sea ice. There are plenty of mechanisms. There have been plenty of explanations trying to explain what could be the mechanism that caused the rapid decline in sea ice, both from the atmospheric perspective and the oceanographic perspective. Since this is a Monsoon Cafe, I want to present you the monsoon perspective of the effect that Indian summer monsoon has on the Antarctic climate via the teleconnection effect. So this paper was published, I think, last week, 1st September. They say that in the Indian box, the diabatic heating has increased. Because of the increase in diabatic effect, the Hadley cell has shifted north. Because the Hadley cell is shifting north, it triggers some kind of Rossby wave train near the masculine highs, and that Rossby wave train travels along the jet stream to create sea level anomalies all along the Antarctic coast. So these sea level anomalies drive temperature anomalies, which again induce the effect of loss and gain of sea ice in places. For example, this blue patch was corresponding to the Amundsen Sea, where sea ice was increasing, if you remember. So this corresponds to a decrease in sea level temperature. But the other places, it's more or less increasing uniformly. One question which I have with this paper is their Hadley cell diagram. The black lines, the black contour lines, both solid and dotted, show the structure of the Hadley cell taken on a box 70 east to 100 east, from 30 knots to all the way till down. And they have taken the climatological mean Hadley cell. So they have taken from the year 1980 to 2024, I think. One question I have is, it shows that the climatological descending branch of the Hadley cell is around 10 south, which I found it very hard to believe. The ascending branch of the Hadley cell is around 10 south, which I find it very hard to believe. Because if you take the Indian box, your ascending cell has to be somewhere at 5 north, 10 north, right? I mean, this shows that there is, yeah. No, this is JJ, June, July, August, September. So they show that it's at 10 south. Even if it is winter, I think it should be still 5 north, 0 north, right? It should not be. No, I'm saying if it's but yeah, this is what was their explanation. But again, I mean, if you look at the data, you come up with some kind of explanation. But yeah, this is the monsoon perspective of why Antarctic sea ice is retreating post 2016. But again, they have not explained why the diabatic heating is increasing in the land, by the way. So
What is the wrong extreme here average?
they have taken 70 east to 100 east, average along those longitudes. So yeah, that's it.
So what's the impact of Antarctic melting on AOC?
Yes. Antarctic melting, if I don't have ice, if I have an ice-free Antarctic, your convection tends to shut off. Once your convection tends to shut off, your Southern Ocean circulation, your ACC and all those circulation tends to weaken. Once they weaken, your AMOC will shut off. I mean, or weaken at least. It's very analogous to what is happening at the Arctic.
There's also PMOC in the Pacific.
Yes, yes.
So that's also affected by Antarctic melting.
Yes. Because if you think about it, the AMOC is driven by both Arctic ice sheet and the Antarctic ice sheet. But Pacific and Indian, they are majorly driven by the Antarctic ice sheet. So I think the biggest loss, if you quantify in terms of ocean overturning, the biggest loss would be in the Indian sector and then Pacific and then the least in the Atlantic sector, provided there is no change in the Arctic ice sheet. Thanks. That's a good question. So let's say you have a beaker of water. You freeze the beaker of freeze the water from the top. So you tend to form sea ice from the top layer. So as ice forms, it ejects out salt. That's brine rejection.
It's increasing.
Yes. Yes.
But here, same time you see sea ice formation is not.
Reducing. Salinity is increasing because you're supplying warmer and saltier waters from the tropic and subtropic.
You have a magnitude. How exactly? So how much quantity will you quantify? How exactly? How much is increasing?
Salinity, yeah. Sorry. I mean, this tells you the winter time salinity anomaly, if that helps. I mean, the perspective of this plot is in the winter time, you should have saline waters. But in the anomaly sense, your salinity is increasing and your sea ice is reducing. Sea ice formation is reducing. It's still becoming saltier, right? I mean, if there is no warm and cold waters coming from the below, your salinity anomaly has to reduce because, but as you said, brine rejection is reducing because sea ice formation is reducing. But we see that salinity is also increasing and ice brine rejection is also reducing. So something is increasing at a much faster rate than the brine rejection salinity. And that something is the supply of warm and saltier waters from the tropics and subtropics. Thank you.
Yeah, the monsoon is going on quite well. And this was the data provided. But today's rainfall, that is this morning, is the lowest we've had in a long, long time. Okay? The temperature is well there, but still in September, we are 34% above normal. So we're doing quite well. But next 20 days, it may change. And cumulative, we are at 8.3. But I want to compare with what predictions climate made in May 2025. They said June is -4%. They are wrong. They said July is +2%. Not bad, 5% here. August +8%. is plus 5%. I would say with an error bar. September plus 4%. Of course, we have only 10 days of data. We'll see. But if you do the JJAS, errors will cancel out. I think you'll get the right answer. Okay, that's the advantage of averaging over 4 months. Your errors cancel out. Now, look at the rainfall last 1 week. This is the observation. This is the forecast, and it's quite good. Fish to pattern, and even departure. This is 48%. This is 44%. I would say extremely good prediction of last week. Okay, but this has created a lot of media hype because the amount of rainfall in Kashmir, Rajasthan, Gujarat, parts of Gujarat, and also Pakistan is very, very high. Okay? So the question is why? Now, in today's fashion, everything has to blame on climate change. Okay, so there's a climate change. Let's see how much truth is in that. Okay, now if you look at the core monsoon zone, yeah, we went through a bad period in August. They recovered very nicely in late August and September. 10th September was terrible, but it's supposed to recover. We'll see that. Now, if you look at 1st to 31st August, you still see this region is very, very high. Because rainfall around is very high here, and it came in very extreme spells. Extreme spells in Rajasthan, Jammu and Kashmir, and so on. So the question they're asking is, what caused it? Now, this is 7-day precipitation from 30th August, 6th September. You can see clear in the India-Pakistan border, there is essentially a lot of rainfall. Okay, you're talking about in 1 week, 150 millimeters, which is very high. Okay, so because of that, of course, media has to create a hype. That is their job. So, like the cloudburst story about 2 months back, Down to Earth, all of you know that magazine, said monsoon 2025 is on account of a surge in western disturbances intensifying Himalayan disasters. Okay, this is a grand statement with no real proof. Now, there is some, what do you call, logic to it, because people have been arguing for the last 20 years. Because of global warming, all of you know that the polar regions are warming much faster than the tropics, right? So the gradient is changing. If the gradient is changing, the jet will change. I'm talking about the subtropical westerly jet. If that changes, it will affect the Indian monsoon. That is the logic. Okay. Now, you must know the definitions that are used because we focus only on southwest monsoon. Okay. We don't worry what happens in the winter. That's because winter monsoon is not that exciting. It's very straightforward, simple system. And that is governed by what is called western disturbance. Cyclonic circulation in the middle of low troposphere or low pressure area, which occurs in mid-latitude westerlies and originates over the Mediterranean Sea, Caspian Sea, and Black Sea and moves to India. Okay. According to IMD, who do most synoptic analysis, they argue that all the water for this western disturbance comes from these oceans. Okay, that is a wild guess with no proof. Okay, I'll show how it should be done properly. Today, it should do it much better. We can't be just making it's coming from there, so what is from there not true. Okay, now if you look at the amount of rainfall that occurs in December to March, the winter season, where the western disturbance dominate, you can see whole of Afghanistan and Balochistan are all 100% rainfall from. So these desert areas essentially have no real summer monsoon. They are totally dependent on that short season in winter where snow falls. Okay, but look, come to India, it's almost down to 30–40%. But this is very important. This is where the big growing region of India is. This rainfall is very important, but predicting this rainfall is much more easy than the summer monsoon because it is not deep convective system. Okay. Now, here is an example from a very nice review paper by KMR Hunt, published 7 years ago, looking at various kinds of western disturbance, various types. There's one type with a very high rainfall, But that is about 4 millimeters per day, not very high. For summer monsoon people, 4 millimeters is nothing. It barely good evaporation, okay? But it does provide rainfall in dry regions. Now, he has done complete tracking of these WDs, and you can see they are mostly going over India. Yes, here they come all the way here. Documented 3,090 tracks. Okay, and he plot a density. You can see it's mostly in this region. Very nice piece of work. Now, for you to understand this system, because we don't discuss it in our courses or in our research, it's a typical system which occurs mid latitudes. It always moves west to east. Okay, and so this is a front between cold air, warm air, and the rainfall also from front. This is very easy to predict. Okay, as long as you know where the front is, you know it will rain there, and the rainfall can't be very, very high. Cannot be 100 millimeters per day, for example, because it's this system. Let me show a little bit more about it. Now, the other interesting phenomena happening in the last 20 years is Arabian Sea has become warmer. So we used to normally get depression going up the way we go. Monsoon trough. This is the standard story. But now you're getting these. And they are coming in and they're also interacting with the westerly jet. So that is the new complication. And the problem is that the depressions are very well documented by IMD. You can see it on a weekly basis. This year, ones are all given here. But WDs are not tracked in summer. In winter, they are tracked. In summer, because it's very rare. Okay, how rare is it? Now, here is a very nice document of a hunt. He's showing highly intense WDs and high and low intensity here, and along the calendar year, starting August. Okay, you can see August is only 3 of them. September 3, October 10, 13, 20, around 20, or that comes down. So no wonder nobody looks at summer because it's mostly a winter phenomenon. Okay? Now it's changing. That's the whole point. Well, other way of showing this is a plot. I don't like this plot because this PDF has a funny units. One, not one. I don't know what it means. How to scale it to one. Anyway, the point is that in the winter, there are many more WD factor, 4 or 5 more than in summer. Okay? That's why in summer we don't worry about it normally. Now, to understand this, you must know the basics of meteorology, which is that in the tropics, it's hardly any visibility. Absolutely nothing. Not the surface, but I'm talking about 8 foot below and down. But as soon as you go beyond 30 miles, there's a large gradient in both hemispheres. This is what drives me westerly jet. Okay? Here, the jet will come not by gradient, but by heat released by latent heat, by monsoon. The monsoon is not there, there will be no tropical estuary jet. Okay? Now, to show you that you can always see the WDs in satellite data, look at windy data. This was taken long time back, 22 years ago in November. Very nice line, absolutely beautiful. I love to watch it going. It moves every day so much distance. Okay, this is so predictable that the forecast is so good you never hear about it. As a matter of fact, I remember about maybe 10 years back or 15 years back, there was an international advisory committee to MOES, to which Tim Palmer, the famous guy from England, was invited. And we had a meeting with the minister in the evening around 6 p.m. Okay, so being a very smart person, he pulled out his laptop and told the minister the meeting starts at 5:30. At 6 p.m. it will rain in Delhi. And it rained at 6 p.m. Okay, that's how accurate this is. Absolutely moves like a steady system, and rainfall is not very high. It's very nice agriculture, just drizzles a lot. And so this is the system which people study in winter, but the number of papers published is very small because they find it not interesting. Okay, so the way to understand this is when a warm front and a cold front meet, the warm air is lighter, it will rise up. It contains more moisture, it will rain. That's all. Very simple. Okay. there is no convergence of moisture there. It's meeting of cold and dry air. Now, Hunt's paper has a nice review. I think this is about Result 1, 2025. He identifies various WDs in the world. We are the largest. India, Pakistan, Afghanistan, and so on. Others also there, but not so much. Okay. So even for us, it is only happening in winter. Now, what he has done interestingly is he has compared the correlation between sea surface temperature and the western disturbance frequency. How many of them are there? That's very interesting. It is related to what's happening here, which we discussed last few times. So this region, which is very warm this year, seems to affect the WD. Okay. So my suspicion is that we are getting a lot of WD this year, even in summer, because of that very warm pool in North Pacific this year. Okay. It also depends on Atlantic, not surprising. It's coming from there. Also, some dependence on southern hemisphere, which I don't understand. Okay. They may all be connected to circulation. Then he has done a nice cartoon. I won't spend much time on it. A lot of details here. I would like you to read it because it's a very nice review paper. And it shows how the tropical and the mid-altitude systems interact. Okay. Now, here's a very nice 4 cartoons. Okay. One is that this is your depression coming from the Bay of Bengal. This is the WD coming from mid-latitude. And one possibility is that they merge. Okay. This is a simple fluid mechanics logic. 2 vortices are going in a stream and they can merge. Okay, that can happen. The other one more complicated. They interact and go to the jet stream. This I don't understand the details of this. You can look at the paper. They're not merged, but they interact with the double jet stream. The third one is very interesting, which is that the tropical depression supplies moisture to the WD. Okay. Now, this is very important because I can remember it very well. In June 2013, I went on a trip to Badrinath. Okay. I made an error. I looked at the climatology. Climatology is that by June 13th, there will be no rain in Uttarakhand. Okay. And I've trekked many years there, so I know it. Unfortunately, that year, there was interaction between this and this. And both Uttarakhand and Himachal had the worst rainfall of all time. Okay. About few thousand people died in Kedarnath in that zone. Okay. So they had a lot of discussion on that. So this one example where the moisture, which is very low in WD because it's from mid-latitude, is getting moisture from here. And the last thing more interesting, there are occasions where WD supplies moisture, which I'm a bit surprised, but I think it depends on circulation. If WD causes a wind to go over Arabian Sea, pick up moisture, yes, it can strengthen the tropical depression. Okay, so very nice idea. I'm not discussing in great detail. I want you to look at the paper, first class paper. If you have problem getting it, I can send you. Okay. Now, what he says in this paper published this year, he has used isotope analysis, which I think is the right thing to do this year. Look at the isotopes of water in the various oceans and what is the isotope of rainfall. Connect the two. Okay. Based on that, they are saying that the rain of the WD comes not from Mediterranean or Black Sea, comes from Arabian Sea. Okay, so there is a very new result. Okay? So the opposite of what IMD was saying. IMD was saying it without any proof. They don't have any data. This guy has done, he has quoted, and he's not done all the way, he's quoted. Now, to show that this is happening this year, here is an example of 500 millibar vertical motion averaged over 10 days, so that you get a rough idea of the synoptic system. We get 2 of these. This is WD, this is PD, and they are interacting a little bit. Okay. So this is true in June for 10-day period, July, sorry. In 10-day period, there was interaction between vertical motion and WD and here, and we had a lot of rain in Pakistan, Afghanistan, and so on. Now, because we don't discuss this much in our courses and in our research, I wanted to understand this very nice structure. It's most unique to India. Very high. This is July this year. easterly jet and westerly jet, and they are separated by a very small distance, not even 5 degrees of latitude. Okay. So this point was of great interest to people. If all of you remember, first time TEJ was discovered was in India by Koteshwaran. And so when they realized that the strong easterly over India, upper level, and we know that corresponding westerly, they were wondering how do we interact. Why? If you look carefully here, there is an anticyclone at upper level. Okay. And so these will interact depending on how close they are. You can see a slight shift in this jet or that jet will make it more complicated. So I have not done many years, but I think I want to look at many years data to see the relative position of the westerly and easterly jet and how close they are to each other. Because they are close, they will interact. This is August. I don't know the full data till 25th. And again, you can see right close to India is over the Tibet is anticyclone. Now I can tell you that I've seen a lot of this work earlier. One of the problems in this work is if you are in the tropics, you all know the simple model, which I like similar models, is a two-level system. Lower level is easterly, upper level is lower level is westerly, subordinate, and upper level is easterly, right? That's a nice picture to have. But if you come near Tibet, you're in deep trouble. Tibet is a height of 4-5 kilometers. So half the troposphere is gone. You can plot it on the analysis, it is meaningless. It is a fictitious thing, okay? So I would like somebody, one of you, to get me sigma level data, not pressure level. If you use sigma level, you can ask whether over Tibet, is there a two-level structure or something else? Here we know two-level. Surface 5 kilometer to 15. Here I don't know what's happening. And nobody has discussed this. And here also it only gives you pressure data. You can never figure out over Tibet what's happening. Okay. You can still do it. If you know the surface pressure over Tibet, you can take ARFI and plot between the surface pressure and tropopause. That you can do. Now, a lot of people have looked at this issue before, how the Rossby wave occasionally dips into India. Now, I looked at this more than 30 years ago. At that time, unfortunately, neither the data was good nor the analysis was good. So we wrote on paper, but I was not happy with it. Now, when this Rossby wave comes down just to north of India, when this winds move like that, that is the disinfection. Now, it's very easy to explain that. There's a nice cartoon which I found in a textbook. The cartoon shows that as the jet vacillates, the jet going straight, it goes like that. So that is the main hypothesis today, that because of the change in the temperature gradient, which was strong 100 years ago, now it's weak. The jet is not anymore stable. It goes in unstable way. It snakes. Okay. When that happens, it comes this way, just by using basic computation, which will show that at this point, it will decelerate and hence cause sinking motion. Here it accelerates, causes rising motion. This is what is causing you rainfall in Uttarakhand, Himachal, and other places. When the Rossby wave comes down and goes back on the curvature, it does that. Okay. So it's very interesting work. I think some more work has to be done. I hope some of you read Hunt's papers and say there's something worthwhile to be done, because this is going to change in the next 50 years. The interaction between TJ and vertex jet is definitely going to change. But I'm not sure how much it contributed to this year's monsoon. I'm not sure because it's not well documented. Okay, let's look at some extreme rainfall years that occurred last week. 3rd September, Udaipur, unfortunately, second time it exceeded 3 millimeters per day. So that's deadly. Just had one in August, and within a few weeks, it was another 300 millimeters. And again, this is definitely a cloudburst because it's 230, 210, all in this area of pilgrimage of Vaishnav area, very tough area to manage people. Okay, so this definitely was an unusual one. And on 6th September, 3 days later, more than 10 stations in Rajasthan and Gujarat, 100 millimeters per day. Okay. So this is very rare because Gujarat are the deserts. Normally you don't get this kind of rain. But when it happens in a big way. Now, one more data I have, which is 7th September, again Gujarat, 240, 230, 210, 170, 150. This is a huge rainfall system. And I know that from people who live in Ahmedabad and Gujarat, when this happens, entire rail tracks are washed away. Because remember that when you live in a desert, that ecosystem has not been designed to handle large flow. Okay. In other parts of India, the river has essentially, over a long time, made a nice, what do you call, a path for it to flow. But Gujarat is flat. Rajasthan is flat. So when it rains, it just spreads everywhere. So rail tracks are just removed and you'll go back and fix it again. Okay. Now let's look at what's happening to Nino 3.4. It's already reached minus 0.6. Okay. And so most of this season, starting from 2nd June to 7th September, has been about 0.3, except one period here, mostly 0.4, 0.5. So although we have a criteria of 0.5 for La Nina, but that's arbitrary criteria. I don't think nature obeys that. The fact that that region is cold, close to 0.5, I think is what's causing heavy rainfall in September here. That's quite clear. We saw it last week. I will review that in the last talk. How about IOD? IOD is highly negative, but has had no impact on the Indian monsoon. I'm a great skeptic of this. I don't believe in IOD causing anything. IOD reacts to Indian monsoon. I'm yet to see a proof that IOD actually affected the Indian monsoon. Okay, so this is another proof. Monsoon is getting along fine, very fine. IOD is going more negative. I see no impact so far. Okay. Now let's see how good the forecast was. Pretty poor. Last week was very good. This week is very bad. You can see that the last few days the forecast was too high. Values were 2 and 4 millimeters per day, and they are predicting 6 and 7. It's a huge error. Okay, so I think it has to be, and this is not the only IMD model. Also, ESMW, then the instrument, all of them have this problem. I don't know why. All of them predict too high rainfall. It didn't happen. So if you go by this, if the actual rainfall the next 20 days is normal or below normal, well, I don't know what will be the monsoon like. We are going by forecast, it looks good, but if it next week is like this week, we don't know what's going to happen. Now, this is a prediction from today. You can see that they are saying picked up, and it's remarkable that in September they are saying it's going to rain 9 millimeters per day and the average is 6. This is 150% above normal at an all India level. This is huge. Okay, so if this happens, of course, September will be like 2019 and 2020, very high rainfall. Okay, now this is GFS to show you that even ESMW has the same forecast, actually even higher. It goes up to 12 here. Double the rainfall. Okay? So that's surprising. We'll watch next week what happens. Now, what is the spatial pattern according to both GFS and ESMW? All are saying that this is a region going to continue to get high rainfall. Okay, bad news for them. We already have been pelted with rain. More rain is coming. And here, slight difference between GFS and ESMW. And here also there is slight. Karnataka is saying below normal, this is saying above normal. We'll see who's right next week. Let's look at the pattern given the ESMW spatial pattern, which is nice. So we are next week here. You can see that the western part will get rain, eastern will get dry. That is the forecast. Okay. Again, these are all large scale. I'm really impressed by this thing this year. And nothing is small scale. Everything is has a Asian scale. Okay. Now this is the next week, pretty much the end of the monsoon. It's slightly weaker, and there's a lot of negative number here. So if this is right, the number will be around 180 to 90 millimeters. If it is wrong, it'll come back to maybe 160. Now, what's interesting is you can go to October, all the models are saying October will be above normal. Okay. Now, this is another interesting story developing. It looks like for the last 20, 30 years, rainfall, monsoon level is extended beyond September 30th. So there are a lot of people debating, should we use calendar year as a criteria or have some other criteria for the end of the monsoon? Because this is amazing. In the first week of October, then are crazy. I'll tell you why I find it interesting. In 1985, 40 years ago, I had gone trekking in Uttarakhand to a famous place called Tuganath. It has the best view of the Himalayas anywhere in India. Okay, you can see the entire from west to east. I had gone there 2 years earlier, and that was in June, and it was raining all the time. We didn't see anything. Okay, we came back very disappointed. So I went again, second time. This time I went in October, hoping that October monsoon would have gone. On the first day I arrived, it continued to rain. I was really annoyed that my plan went wrong, but the withdrawal of monsoon in Uttarakhand was on 11th October. So on 10th October, I and my friend were annoyed that we are not going to say anything. And next day, it was completely clear. And the view of the Himalayas we got was mind-boggling. I would call it an experience which is not ordinary. Okay, so I remember this very well. And I came back to Bangalore and checked. Yes, the onset was a little delayed that year, 1985, and that's why we had a rain till about 10th October. Then it withdrew, but this year, according to ECMW, it may go in beyond 10th October. Okay. Now let's look at IMD forecast. IMD forecast for this week, current week is 11%. Next week is 13%, very good, above normal. And this is the last week of September. It is 9%. And like ECMW is saying, even in October, it is positive, 15%. So from all this, two independent forecasting system looks like we will have a good September, but we will see the next 2 days what will happen. Okay. Now, before you ask questions, I must remind you that next week is Tanganaka, right? Tanganaka. And then last week is 24th of September because the week after is 1st October is a holiday. So we end our discussion on 24th September. Okay. Are there any questions? You're welcome.
If it stops rain now,
Huh?
if it doesn't rain anymore from after today,
Huh?
if it doesn't, after today it doesn't rain anymore, what would be the annually?
Oh.
Because already possibility is close to the normal, right?
Yeah, but I don't think it is strawberry. No, it's something like break. So we don't depend break is number. But I suppose that's a little bit trouble. So right now 840 millimeters. So it will be normal, but that is normal.
Yeah, that's right.
So I don't think all marks can go down. All marks will go. So we'll see next week. The next week will do the issue. Today is 17. Another 1 week of game zone. Okay, thank you.
Is the monsoon extending or extending?
Huh?
You mentioned